Hello, everybody. I'm David Kaminsky here with Bryn, Tanner, and Kevin for group number 1. For our final project, we are going to present our design study of a rear-wheel drive electric vehicle drivetrain. At the beginning, we laid out a few objectives for ourselves. We successfully modeled a kinematic simulation of our design in CATIA and ran FEA on our critical components. Then we compared our results with our own calculations and found a way to incorporate what we learned this semester into our data as well. At the end, we changed a few parameters of our system just to see what kind of effects we could produce. So we benchmarked specifications from a Tesla electric vehicle to use, and we came up with our own calculations for our design. These included motor outputs and a few of the major forces acting on the vehicle. We did research on what kind of materials are commonly used in gear design and found this common heat-treated carbon steel that we would use. We did the same thing for our drive shafts and decided on this material. When we started, we theorized that the highest concentration of stresses would be seen in the gear shafts. We figured this because the gear train is designed to increase torque. Tanner came up with a great design for our drivetrain and modeled it in CATIA. Together we worked on an assembly, and from there I created a kinematic simulation, which I'm about to show you guys. So I'm not sure if you guys could see that very well over the internet, but if you can, you'll notice that the gear shaft rotation speed decreases down the gear train, producing an increase in torque. So with that, I'll hand it over to my colleague.
Hello, I am Bryn, and in this portion we'll be looking at the finite element analysis. For our system, we had to break it into the basic components in order to really look at it in a static case. And for our software, we had to actually apply the rotational forces to the point of contact where our part will interact with a different component. So that's where we'll be looking at with this. And the CATIA does a very decent job of showing where the stresses are going to build in the part, as seen in these pictures here. We have the von Mises stresses, and then we have the displacement stresses. The displacement in this case is a resonance, so as the part rotates, it will go at a certain frequency, and that's where this displacement is coming from. So in this slide, we have our first gear, which is connected to the input shaft, which is directly connected to the motor for our torque and our power. This slide, we have gear 2 and gear 3, which are connected by an intermediate shaft. And we can see that the stresses are mainly along the shaft and along gear 3 because they have a smaller diameter. And lastly, we have the CV axles. They are going to be transferring the power from the gear train to the tires, and as such, they would be building up the stresses at those two terminals. And in this next part, we'll be looking at the more mechanical aspects of the components that are leading into the parametric study. Here we have a few basic equations that we had learned in class in order to kind of relate that to the components that we'll be analyzing. So in this slide, we have a few results from the calculations, being the shafts, mainly the CV axle and the gear connection, which are connecting from the gear 2 and gear 3. Our two basic set parameters would be the diameters of the shafts, and we have our yield strength on the two materials that we had chosen from them in the previous slides. So here we were able to calculate the torque, velocity, polar moment, and the angle of twist, all resulting in a shear stress that it is going to go under, which relating to the yield factor, or the yield strength that we have here, we're able to calculate the safety factor. The CV axle being around 1.23, and then the gear connection being around 18, which is pretty significantly high for this. When considering the gear train, our main concern was the gear ratio and the output torque versus the speed that we needed. which will be discussed later in a separate slide. But here we have the main calculations that led to the ratio and the final torque, shear stress, and safety factor, which are based on the material yield strength and the material properties.
Hi, I'm Tanner Kuhn, and I will be discussing some aspects of our project pertaining to the transmission, starting with the shear force and bending moment diagrams of the input shaft. Here we can see how the bending moment and shear force diagrams were created, similarly to that of the gear train example discussed in class. Only the first shaft will be analyzed in this presentation for the sake of time. The force that is applied to the center of the first gear is the amount of torque applied by the motor divided by the radius of the gear. Knowing that the shaft is supported by thick bearings on both ends and the force applied has been calculated, the shear force and bending moment diagrams can be illustrated. The angle of twist was found for the 6-inch section of the shaft that connects to the power output of the motor to the first gear. This simulates a worst-case scenario from a forces perspective of the brakes being engaged as the full torque of the engine is being applied to the shaft. This scenario was used for all static cases in this project. The same processes was applied to other critical components as well. For the gear train, in order to achieve a similar gear ratio to that of our reference vehicle, the Tesla Model S75 of 9.73, the number of teeth per gear is as follows, and a gear ratio was found 9.75 to 1 for this project. And the diameters of the gears for our gear train model were calculated based on these gear teeth numbers, as well as the tooth size and circular pitch, though force studies were not conducted on the gear teeth for this project. As for the torque increases due to the gear train, the input torque of the engine was 325 foot-pounds, which is equal to 3,900 inch-pounds, which is in turn increased by the gear reduction to 37,254 inch-pounds of torque. This increase in torque via a single gear is an advantage of electric vehicles over internal combustion vehicles, as the maximum torque of the engine is provided at low RPM, practically from a standstill, meaning multiple gear ratios to achieve a narrow optimal torque curve like that of internal combustion motors is not necessary, and the high angular velocity output capable from an electric motor means that no overdrive is required to maintain a higher velocity. Parametric study was a large part of our project, as it was used to determine the final design of the drivetrain and its components. The critical or most vital components we deemed necessary to optimize through parametric design study were the input and intermediate shafts of the transmission and the axles of the CV axles. The diameter of the shafts, both in the transmission and axles, directly correlated to the amount of stress that they could endure when subject to high torque during acceleration and especially when braking. Shafts with higher diameters can transfer a larger torque for the same amount of shear stress, but weigh more and potentially cost more as a result. The material in which the shafts are made also can yield similar results, as the materials with higher yield and tensile strength can be used on smaller diameter shafts to achieve the same or better stress displacement at the same torque. The gear design and ratios were also subjected to a parametric design study to achieve an optimal angular velocity output to the wheels from the motor. If the ratio increased, then the RPM from the motor is reduced while the output torque is proportionally increased and vice versa. The input shaft was analyzed by changing the material used in the simulation to find an optimal material to use. In our case, S45C heat-treated carbon steel, as it is commonly used in car transmissions and is more machinable than the closest competitor, which will be discussed by Kevin in the following slides. Thank you.
Hi, I'm Kevin. To elaborate further on the parametric analysis, we additionally tested changing the input shaft material to AISI 8620. This allows the shaft diameter to be decreased. This can also be done for the rest of the components in the drivetrain in search of optimal performance of the parts. Here we demonstrated this test being run in CATIA. As expected, we observed a higher deformation in the original material than in AISI 8620. Next, we analyzed the performance efficiency using the equation power in divided by power out, finding that the drivetrain is 97% efficient. The loss of performance can be accounted for in the heat friction between gear teeth. Following this, we analyzed the MSST theory of the system. The results of this can be seen on this slide. It should be noted that the gear used for this analysis was gear 3 because it was the smallest gear. Interestingly, we noted that the highest percentage difference is 22% in the gears and the smallest being 8% in the CV axles. To conclude, we observed the main power losses were due to frictional heat between gears, and we found that the selected materials in the system were sufficient for our application. Lastly, it should be noted that the gear reduction increases torque, which is the opposite effect the gearing of a combustion engine has on its torque. Here is a list of the sources we used for information on this project. Thank you for listening. Any questions?